Hello everyone, welcome to AI Anytime channel. In this video, we are going to explore the hyperparameters and training arguments. Those are required when you fine tune or even if you train a large language model or a language model. Okay. And we're going to look at the training arguments, which is available in the Hugging Face trainer class. And we're going to talk about a few things in detail. This is more of a theoretical video. Okay, so if you are familiar with fine-tuning LLMs, do not watch this video. Don't waste your time to you know like to watch this video. Okay, this video is completely beginner friendly. Okay, who has just started their journey with fine-tuning LLMs, and they are a bit overwhelmed with terminologies like batch size, gradient accumulations, weight decay, optimizers, learning rate, evaluation steps, evaluation strategies, and things like that. If you look at a fine-tuning notebook that you will find it on the internet easily nowadays, also on my GitHub repository. How can you decide that the optimal value or the categories for a given hyperparameter? How do you perform this trial and experimentation? How do you decide the batch size? How do you pick a gradient accumulation step or a strategy? I'm going to cover these few basic intricacies when it comes to fine tuning LLMs and deciding the optimal hyperparameters. I do have a crash course video on fine tuning, which is like 120 minutes video. You can also find that in description. I'll share the link. Now, this video is only focusing on the training argument, the trainer class in Hugging Face. So if you are performing an SFT or DPO or whatever, different techniques or methods when it comes to fine-tuning LLMs, I will cover a few topics in this video. So uh, without any further delay, let's jump into the Colab notebook and my screen grab to show how I'm gonna explain this theoretically and also spelling it out in a code as well. All right. So guys, if you look at here on my screen, I have Google Colab over here, and you will see a piece of code that is using something called training arguments. Okay, it's part of the trainer class in Transformers library. I'll show that, and then you have bunch of parameters that we're gonna talk about in this video. And if you look at first here, the training argument, this is part of this trainer class. If you look at here on the Hugging Face documentation, it says the trainer class provides an API application program interface for feature complete training in PyTorch, and it supports distributed training on multiple GPUs and TPUs, mixed precision for NVIDIA, and blah blah blah. Okay. Now they have different modules within this class. Okay, so if you scroll down, you will see a bunch of functions, modules, whatever. Okay. Now here we're going to talk about this, why the hyperparameters are important, and you should understand, you should not only copy paste and just take somebody else's notebook and fine tune it, because that's not the real machine learning. That you are not doing a machine learning over there, to be honest. Okay, so to understand each and every parameters and their significance when it comes to fine tuning LLMs. Okay, now when you talk about the hyperparameters, they are settings or configurations that are used to control the training of machine learning models. It's not a new term. We have been seeing it in machine learning earlier when we used to you do deep learning with neural networks and things like that. We always used to say, let's do hyperparameter tuning. So now, with LLM coming in, people are probably not talking about that much. I've seen this, but these are really important. Okay. And they are set before training begins and can significantly impact the performance of the model. So keep this in mind, right? When you fine tune an LLM, it's not a one time task. It's a trial and error experimentation. You have to keep tweaking these variables, these numbers that you see on the screen, and try to find out an optimal values for fine tuning. And it's difficult, and that's why it's costly. When you say that somebody is training llama 2 or Mistral, they have to spend millions of dollars for that, because they have to do it multiple times on n number of GPUs and things like that. Now, the main hyperparameters that you see, these are the minimal one that you need here, okay, in Hugging Face Transformers training arguments, and I'm going to talk about that one by one. Okay, in this we'll go through it, and we'll also bring up some diagrams if that is valid. Let's talk about the batch size first. Okay, so I'm going to show it here. Okay, as this is going to be a bit theoretical. Okay, but I'm going to show you that. Okay, now first is First is batch size. First is batch size. Probably I'll just make it a dark background. Okay. Now we're gonna look at batch size at first. Okay. Now what do you mean by batch size? So it's basically refers to the number of training examples used in one step of model training. So I'm just gonna write it over here. I'll just make this a bit change. Okay. And I'm gonna write this here. Okay. Number of number of training examples. Training examples used in one step of model training. That's how we define batch size. Okay, and this is really important. Okay, now the data set that we have now, imagine if you have a data set from Hugging Face or wherever locally, is divided into several batches, and the model weights are updated after processing each batch after each step. Okay, now, choosing the right batch size is of course really critical, critical decision in training a model, as it impacts both the convergence speed, the way model converges the weights, and the quality of the model's training as well. A smaller batch size can provide a regularizing effect and lower generalization error, making the model more robust to the new data, but it makes training process slower. Okay, and more susceptible to getting stuck in local minima. This will probably have been some idea of global minima or local minima, but larger batch size can lead to a faster training by making the hardware optimization of GPU, whatever you are using, like for example parallel processing on GPUs and things like that. But it requires more memory and could lead to a less precise estimation of the gradients that you have. So if you don't know what gradient is, we'll talk about it. Let me just do a bit of separation here. So I'm gonna write is, if you have a smaller batch size, then it will take, of course, more time for training that you have to face, and but it provides lower generalization error because the model has to generalize well. So it has a lower generalization error. That's what the smaller batch size does. But if you have a larger batch size, then it will take more time, sorry, less time, because it will use the parallel processing on GPU, hardware optimization. So I'm gonna write hardware optimization because eventually we'll see everything happening on CPU as well, probably. So I'm gonna write hardware optimization, less time, and then requires, of course, uh, less time, but it requires more memory and could lead to a less precise estimation. Okay, so less time, and yeah. Now this is about batch size, and I'm gonna so as a rule of thumb, you should increase the batch size. Now the question is, how should I select a batch size? So you should keep increasing. So keep increasing the batch size until you get GPU error. Okay, this is a this is a rule of thumb that we have. Okay, keep increasing the batch size until you obtain the GPU out of memory or CUDA out of memory or whatever. Okay, and this is how find out the optimal. And you can also do a pre study of it, because if you are using A100 and things like that, then you can at least approximate something. Okay, that's what you can do. Now, in training argument, if you look at the code over here that we have, if you look at the code, these are your batch sizes. We are saying per device train batch size and per device eval batch size. Okay, now this is how you can set the batch sizes when you are fine tuning a pre-trained LLM, or you are fine tuning a language model. Now, the first one that you see, this one, it controls the batch size for training, and the second one that you have controls the batch size for evaluation. This one that you see. So for evaluation, it only affects the evaluation speed. This part has nothing to do with your training processes that you have in that current session. When it starts evaluating, this will affect that. Okay, but generally we set the same valuation for both eval and training batch sizes. Now, the other findings that I have, for my experiences that I have with fine tuning, okay, and we have seen that I'm just writing the caveat over here. So you should avoid using odd numbers. Avoid using odd numbers like setting batch size. If you have batch size equal 9 or 11, don't do that. Okay. Always keep it even. Okay, like 4, 6, 8, dot, dot, dot. Okay. Uh, because I've seen that this becomes slower, fine tuning than with the batch size. So GPUs are basically optimized for particular batch sizes that we see. Now I'm going to show you something. I have, let me just go over here in my pictures, FT, and I'm going to show you a table. Now I'll make this a bit bigger so you can see this clearly. Now, if you look at this, this is an example of fine tuning Tiny Llama model, Tiny Llama LLM, and it shows this table shows, if you look at it, shows the larger batches yield better models, of course. It also accelerates training. If you look at in the left hand side, we have starting with the batch size 1, 2, 4, 8. Then we have training loss, validation loss, memory consumption, and total time hours. Now, if you do it for batch size 8, the total time take 1 hour 30 minutes or something like that. Okay. Now, the total time basically includes the time for validation, guys. Okay, so we should definitely run validation less often when using smaller batches. Do not do that. Okay, it's not recommended. So in this experiment that you see, we are we get significantly better loss with a batch size of 32. Probably this is what I'm thinking. Okay. However, we can see that the memory consumption might increase. Okay, for that. So on a 16, if you have a 16 GB GPU, so don't use a batch size higher than 16 or even 8. You can do 32, but for that I think you have to use gradient accumulation steps. I'll talk about that in the next section. Okay, but this is about batch size. So this is how you have here, you can see. So we are done with this batch size, guys, and this is the output directory where you save the results. This can be anything. Now if you want to fine tune in Colab, and this will create a results folder and it will save all the checkpoints. So we are done with these three, guys. Okay, so for now here, now I'm going to talk about a few more things, which is important, which might not be here. Okay, so which I might have missed that. Okay, but we're going to talk about that. Okay, now if you talk about maximum sequence length, which is, or the padding, you might see that most of the time we use paddings. I recently did my other video on Orpo where I was saying the padding left, the padding left for flash attention compatibility and things like that. Now what do we mean by that? Okay, so see, when you do batches, right, batching also requires padding training examples. Basically a technique used to ensure all data samples in a batch have the same shape or size. That's what padding does. It's every should be the same shape or size, which is a requirement for most of the machine learning models, to process the data in parallel. So that's why padding is important. Just wanted to cover that quickly, that why padding is important. And some techniques, when you talk about flash attention, you always have to we have to pad left. So let me just write it over here, because padding is part of batch sizes. So I'm not going to cover that in a separate section, but I'm going to write it over here, that if you do flash attention, then your padding have to be left. So I'm just going to write pad left. That's what I'm going to write. Now we can also probably we can also see. Let me just excuse me. Now if you look at the next, which is important, is probably epochs and stiffs that we have. If you look at the stiffs, when you say, let me first cover the do eval true. When you say do eval, it will evaluate the model. It will come up with the it will evaluate, it will come up with the loss, validations loss, and everything. And it takes time when you do eval. When we evaluate after certain steps, it takes a lot of time to do perform the evaluation. Okay. Now when you say epochs and step, let me just write it over here. Number two, let me just write it here, epochs and steps. Now, a training step that we have occurs when the model weights are updated once. So this update happens after the model processes a batch of data. Now, if you have, so let me just explain that. So if you have 1000 examples in your data set and you choose a batch size, for example, now my batch size, let's say your batch size is 100. It would take, so what will be the training steps? It will be 1000 by 100 and that will become 10 training steps. This is what it will become. It will become 10 training steps to go through the entire data set once. It only once. Now each step involves forward propagation, passing the data through the model. So see like this, the data is flowing. Okay, the data points, whatever tensors that you have, probably that will flow inside it. Okay, through a forward propagation, calculating the loss, how far the model predictions are from the actual result, and then use back propagation. Now just use the back propagation to update the weights. That's how we have been seeing in the machine learning modeling, right? When if you're familiar with machine learning, how to how the back propagation method update the model weights in an attempt to reduce the loss. The loss is nothing but the model's error. That's what a loss is. Now an epoch is completed when every example in the training data set has been presented to the model exactly once. So how many steps are in epoch depends on the size of your training data, the batch size, and things like that. Okay. Now, if you look at the above example, like of 1000 examples, and you're using a batch size of 100, it takes 10 steps to complete one epoch. Okay. So it will take 10 steps to complete one epoch. Training for more epochs means exposing the model to the same data multiple times with the hope, with the hope that okay, model will learn the patterns better, it will generalize well and things like that. But it's not always true. It might start overfitting. So it depends on the quality of data, the size of data, and things like that. Okay. Now in the training arguments, let me just also write it down. Probably if that is not there, let me see if that is not there. So I'm just gonna write over here, but you can maintain the order. We have something called numtrain epochs. You can see it showing it over here. And when you say numtrain epochs, I'm gonna write, for example, 3, and then you can have a max step as well. So let me just write the parameter for that, and I'm gonna say max steps equals 1000. Okay. Now, if numtrain epochs is set, if you set this part, then this will be ignored. Okay, so let me just write it over there. See, if non-train epochs is set, max steps will be ignored. So this will be ignored. And and for this configuration, the training will last for 3 epochs. The training data will be seen 3 times by the model. That's how it works. Okay. So this is about epochs. This is about steps. We're going to talk about gradient accumulation steps, which I have covered in my previous videos as well in detail. So if you haven't watched that, I will recommend you to watch my crash course on fine-tuning LLMs. Okay. Here I'm going to write gradient accumulation steps. Now, it's fantastic. The piece of innovation with gradient accumulation, it basically simulates the training with larger batch sizes by dividing the data into smaller mini batches. Okay. So instead of updating the model weights after each mini batch, the gradients calculated from each are accumulated over several steps. So it accumulates the gradients over several steps. And the model weights, and you can see it, we have something called gradient checkpointing true, gradient accumulation steps true. We're going to talk about that. So if you look at this part which says gradient accumulation steps 2 and gradient checkpointing true, and let's talk about that and understand that. Now, so for, let me give an example and then we'll understand better. So for if Let me bring up my cast. Now, if the target batch, if the target batch size is, for example, 124, but if you have an hardware and hardware does not support that, it only supports, for example, 256. This is what it supports. Now, by accumulating the gradients over, so how will you do it? You have to do it. If you multiply with 4, you will get exactly 124. So what you're gonna say then in that case? I hope you will get uh, 6, 4, 24, 5, 4, 2, 0, and 4, 2, 8. Yeah, that is fine. So what we are saying here, what we can say, okay, I will do 4 mini batches. So now it becomes 4 mini batches. You can look at the spelling of batches, which is fine. CHES. Yeah. Now 4 mini batches of 256 samples each. This is how you handle through gradient 256 samples each. Yes. Now the system can mimic the effect of a single update with 124. Yeah, yeah. And so this method balances the need for larger batch sizes, which can lead to more stable gradient estimates and potentially faster convergence, with the, of course, constraints of available memory resources and whatever you have. Now, and I'll explain that here because the question can be, okay, can you explain me about this? You can ask me this question because here we have per device train batch size 4 and gradient accumulation is steps 2. What do you mean by that? Now let's understand this, guys. Okay. Now it means that we are using a total. So if you look at this thing here, per device batch size 4 and gradient accumulation 2, it means that our batch size is 8 here. Okay. So we are using a total batch size. So in case of example, so let me just write it over here. What we are doing, we are saying that total batch size is that our total batch size here is 8. Okay, which is 4. You can just write 4 into 2, and it is equivalent to getting per device train batch size to 8 and gradient accumulation steps to 1. It's the same thing. So if you make per device batch size 8 and you make this 1, it becomes the same thing. But this technique does not affect the performance of the model itself. And of course, you need the uh, you need the memory over there. If you don't have GPU, you have to be really careful with these kind of tweaking. Okay, so if we experiment with the small batch sizes and only one GPU, we will not see much difference in terms of training time. But when you have the larger GPUs or more GPUs, multiple GPUs, then it's really the significance becomes really vast there. When it comes to gradient accumulation steps. Okay, so this is what we discussed. Now let's also talk about the next point, which is let's talk about quickly about gradient checkpointing that you can see we are using in below. So I'm gonna write gradient checkpointing here. Now, this is not a hyperparameter, by the way, guys, but this has been used in training argument, the trainer class. But see, it won't affect the learning pattern of the model. It's just a memory optimization technique. So this has been asked by in recent interviews that I've seen. Okay, in some of the AI first company, they ask about this. So this is nothing but a memory optimization. So let me just gonna write it over here. I'm writing it's a memory optimization technique. That's what it is. And is used for models with very deep architecture that requires a lot of memory. Okay, so if you want to use, which has a lot n number of layers and requires significant memory, then you can talk about checkpointing. The idea here is to reduce the memory consumption by storing only a subset of the intermediate activations, because the activations are being generated during the forward pass. So when you pass the data into a forward pass, there are activations that are being generated, okay, through the network that we have, and these activations are necessary for the backward pass. So when your data starts flowing, from one layer to the other, and when you have a forward pass, for example, then here you will have some kind of activation. So the activation will get generated. Okay, so I'm going to write activations, and these activations are important, for the backward pass when you do a backward pass. Okay, and this computes. So backward pass computes the gradients for the model's parameter, right? So I'm going to write it computes the gradients. and that's how you achieve the global minima or whatever minima that you have to achieve, in your in a training process. Now, let me tell you generally how it happens, right? So in standard training, all intermediate activations are kept in memory to calculate the gradients during the backward pass. But if you and this approach can quickly become infeasible for very very deep networks, because if you're keeping everything in memory and you have a limited memory compute or capacity of most hardware like GPUs like T4 that Google Colab provides and things, then you can't do that. And that's where gradient checkpointing comes in. It tackles this issue by saving activations only at certain layers within the network. And for the layers where activations are not saved, they are recomputed during the backward pass when needed for gradient computation. That's what it does. Okay, so basically it's a trade-off between computation and memory uses. That's what it does. Okay, so yeah, so you can also do, so there are two things, right? Let me just also show you. You can pass it in training arguments over here, and let me just add a cell. You can also do, it has, I remember, it has, what does it has? It has a gradient checkpointing enable or so. Yes, this is right. No, collab, I have collab pro, which gives me the code assistant. Now if you look at it, it says model.gradient checkpointing enable, and that is important because now this function can also help you enable the gradient checkpoint, or you can also pass it like here in the training argument itself. Okay, but you can also do it like that. Okay, keep this in mind, and I'll give this piece of code that you don't have to worry. Now I have a graph for this as well. So if you look at these graph, it says with gradient checkpointing and without gradient checkpointing. Look at the memory consumption. So if you are not using gradient checkpointing, the memory consumption becomes a bit high when you go with a larger batch size. Now keep this in mind that most of the time you will, at least if you are doing a hobby project, you will not go beyond 4 batch sizes, but if you really working in an enterprise or for a big company, and if you want to uh, train on a larger data corpus or a data set, then you have to increase your batch size by 8, 16, 32, whatever. And in that case, you have to use gradient checkpointing. If you look at here, uh, without gradient checkpointing, it's increasing high, and with gradient checkpointing, it's if you look at for 8, it's almost half of it that you see. That is very important. So keep this in mind. So if you read this, I'll just give you a ballpark number that I have in my notes. I can see in my diary. 40% memory consumption it reduces on average. So reduces 40% memory consumption. That's what it does. So I've written it over here. I'll give this screen grab. Okay. So when you are using a consumer GPU, it's necessary, guys, even with the small models. But it does, just keep in mind, it does significantly affect the computational cost for fine tuning. But for a batch size of 8, you can see it's twice as fast, with gradient checkpoint over here. So you should keep an eye on this. Okay. Now I think we are good with checkpointing, we are good with epochs, max steps, we are good with this top thingy, and we're going to talk about now learning rate a bit. I think this is not that is not that complex, because we have been seeing about learning rate from our machine learning tutorials that we have been seeing. It's but people don't talk about it a lot, but this is one of the most critical hyperparameter that controls the speed. So let me just write it here, learning rate. So I'm going to write learning rate, and it's a critical hyperparameter that controls the speed. So I'm going to write control the speed. Simple. At which the model updates its weights during training. It controls the size of the steps the model takes in the parameter space towards minimizing the loss function. And it's really, really important to set a good learning rate. And again, it's a trial and error experimentation. For LLMs, setting the learning rate is even more important because of the large number of parameters and complex data patterns they aim to learn from. A too high learning rate, you don't have to do it because it will start converging too quickly, and you'll find a suboptimal solution, or find a very local minima just when you start training it. Okay. So I'm going to write a few things, guys. Basically it's ranges between it's I will not cover that in too detail because we already know about it, but I'm going to say it varies between 1e minus 6 and 1e minus 3. That's how it varies. This is I have seen in most of the research papers, and the recommended one is, probably you can try it out, 1e minus 3, 5e minus 4, 1e minus 4, dot dot dot. This is what you can vary. Okay. Uh, I'll recommend that you go with 1e minus 4. Okay. Yeah. So this is how you set a learning rate. Let me see what I have, and I have taken from Hugging Face. That's what they recommend as well. You can see, so the learning rate. Okay, and this is fine. So this is okay. Now we have a schedule which where it does go. Okay, here. Okay, LR schedule type that you see, which is says linear. Okay, now I'll cover this with this only because it's a bit associated with this. Now the purpose of a learning rate scheduler is to change the learning rate according to a predefined plan during training. Now this can help because see the problem with neural networks in general is that it is basically stuck in a local minima or overshooting the minimum. Okay, now this approach can help to avoid getting stuck if you have a predefined plan that how to tackle that. Now if you say linear, what do you mean by that? Now most huge type or scheduler is warm up based. So when you the learning rate starts from a smaller value and gradually increases to a predetermined value over several epochs or steps, and this is how you probably handle it. Okay, now in most cases, the industry has been recommending a linear scheduler with warm up since it has been shown to perform at least as well as other scheduler. Okay, now there's a paper also. Probably let me search that paper. That paper name is adaptive learning rate. uh, It was by refinement. Okay, yes, this is the paper. When, why, and how. You should read this paper. I will give the link in description. This is a research paper where they talk about uh, you know how to adaptive learning rate that you see. Okay, it has been you look at the author guys, and one from FAIR, Facebook AI research team, Meta, Google Research, Samsung AI Center, Boston University. So great team, fantastic. And they come with this research paper, and if you read this, you will understand. You will develop a better understanding of how to do that. Then now you can ask me a question. Okay, you are only telling me about linear. What about others? So you have cosine. You can also try it out cosine. Cosine and linear yield a similar, most probably a similar training loss, but linear seems slightly better in most of the configuration. So, but you can try it out. It depends what you want to do with this. Okay, so you have cosine as well that you can try. So I'm just going to write this. Now you can see we have something called warm up ratio, warm up steps, and blah, things like that. Okay. Now let me just write over here. What do you mean by warm up steps, and ratio? So we have warm up steps and ratio. Now these are the training steps during which the learning rate is incrementally increased from a lower value, which will be initial lower value, to a predefined target learning rate. Okay. Now I'll give you an example. Okay. Let me first see it over here what we have. Okay. We have warm up ratio at 0.1, which is fine. Okay. Now let's come back over here. Now imagine if we have 1,000 warm up step. So the learning rate starts low and increases with each step until it reaches the target rate at step 1,000. Now after it reaches this 1,000, the learning rate may follow a different schedule, okay, such as a constant rate or a decay. So basically you set up a warm-up step and ask the learning rate to first start low and increases with each step and reach this value. Once it reaches this value, you can then have a different schedule for that. Okay, now instead of specifying the number of steps, the warm-up ratio defines the proportion, which is better. That's why if you look at here in the training arguments, we have something called warm-up ratio over here, and that is important. Uh, so if the total training is planned for example, now let's make the example increase that to 10,000 steps, and the warm-up ratio of 0.1 is used, then the first 1,000 steps, which is 10% of the entire 10,000, are allocated for warming up the linear rate. Now this ratio basically helps in scaling the warm up period according to the total length of the training, ensuring the warm up phase is proportionally adjusted for different training durations. And this is important, guys. So this is what warm up is doing. So a good rule of thumb is that to set the warm up ratio to 0.1. but you can again find it out depending on how big your data is and what kind of compute you are using. So I think we are done with this also. We are done with all of this. Let's talk about weight decay a bit. We are okay with this. We are eval step is a very common thing. Do eval, I explain that. Okay. I think we are talk about a few things and then we are good. When we have optim, we have weight decay. Now weight decay basically penalizes the larger weights in the model's parameter. Okay. Uh, Increasing the model to maintain smaller weights. Now this is achieved by adding a term to the model's loss function that basically includes the sum of the square of the weights multiplied by a regularization parameter. So you know how to regularize a model, right? Earlier you would have seen it in neural networks. Okay. Now by default, if you look at the Hugging Face documentation, the weight decay is set to 0.1, and I recommend that probably you do it 0 unless you observe some overfitting of the model. So when you start overfitting, you can play with this number that you have for weight decay. Okay, that we have. So I'm not going to talk about that. I'm just explain that. Now optimizer is important. So let me just write optimizer, and we're going to talk about optim that you see Adam W8 bit. I have covered that earlier also, but I'll just cover it, guys. Okay, really important piece. Okay, so I'm just going to first write all the optims that I can remember, that I'll forget. So we have Adam, and I'm going to write W. And then we have add a factor as well. Add a factor. These are the three that I have probably, I've been seeing it. Okay. Now, an optimizer helps in training models by minimizing errors or improving the accuracy of the model during fine tuning. Many optimizers have been proposed, but Adam W, a variant of Adam, is by the most used today. Now, ADA factor can also be used as an interesting alternative for memory efficiency, but just explain that quickly. Now, ADAM is a full form of adaptive moment estimation, maintains two moving averages for each parameter, so one for the gradients and the other one for the square of the gradients. So basically takes a lot of memory. So I'm going to write lot of memory consumption. Now, Adam W, it's just a variant, as you can see. Now, it's basically it's an acronym for Adam with weight. I was interviewing a guy and I asked him, he was talking about this is what I have been using. I asked him the full form of it. It says, I don't know. So that's what I'm saying. You guys have to understand these terminologies, right? So the second is Adam with weight. Basically, it's not only weight, it should be weight decay. Now, Adam W basically decouples the weight decay from the optimization step. So basically reduces the memory consumption a bit. Okay. It provides better training stability and model performance. Okay, that's what it does. Now, ADA factor is designed to reduce memory uses. It achieves by factorizing it's a bit of derivative. I'm not going into a mathematical term, but it's factorizing the second order moments used in this one, Adam. Okay. But I will not talk about it because we are good with Adam W. Okay. Now the good thing about Adam W is that it can be even paged to the CPU RAM, to further decrease the GPU memory consumption. So keep that in mind. This is very important. Okay. But when you use LoRa and stuff, probably that significance becomes a bit smaller. Now, what do you mean by this value, guys? You can ask this question that you have here something called Adam W 8 bit. Now, the combination of paged Adam W 8 bit with LoRa dramatically basically reduces the total memory consumption and makes it suitable for consumer hardware. Okay. uh, 8 bit, because you're talking about a quantized there, that's what the 8 bit term is. If you don't want a quantized, I don't know if probably if you have seen it, if you want to do a full fine tuning, then here you have to write it like this. Okay. uh, you have to write it like this. I believe you have to write it Adam W torch if you do a full fine tuning, okay, which is not quantized. So if you have great memory compute with you, you go with this. You should not probably use Adam W 8 bit, but then it's a last resort. So you can do that. Even if you are getting out of memory, guys, now most of the time you get out of memory. Okay, you can also try changing to paged Adam 8W. So I'm going to write paged. Okay, I'm writing it over here. Let me go back to my screen grab. Paged Adam W 8 bit. That's what you should do. Okay. It will be, of course, slower, but will further reduce memory consumption. This is very important. I just wanted to explain that to you guys. I think we are okay with this. So we covered Optane, we covered all of these so far. Okay, up till here we have covered, and we have covered this. This is fine. We have covered learning rates. Logging is for how many steps, after how many steps you log the values and everything. This is fine, Optim. The thing is, let's talk about these two things, FP16 and BF16, which is float 16 and B float 16. This is very important. So I'm gonna write F16 and BF16. This is what we're gonna talk now. Okay. Uh, it's see, machine learning models earlier used to be trained with full precision. So we're using something called float 32 data type. So if you have one float 32, so let me just write one float 32. Now one float 32 consumes 4 bytes of memory, which is 32 bits. 4 bytes of memory. This is what it is. Okay. So let me just go back to screen because I'm going to explain that on screen grab. Now let me explain that, guys, because this is very important for you. I think you guys should focus on this part. Now imagine you have a 7B param model. Let's take 7B param Mistral 7B. Mistral 7B 0.1 instruct. If you have these LLM, so if you use float 32, then we need a GPU of at least, but this is not the exact number. There are other caveat to it, but these are the minimum thing that you need, 28 GB of memory. See this. But it's impractical for even larger models. When you go 30 beats, Grok has been around, I don't know, 500 odd B or something. Okay, just imagine how much compute do you need. Now with float 16 and B float 16, we divide the memory consumption by 2. So just cut it by 2. If you cut this by 2, then we'll have around 14 GB of memory that fits in your Google Colab if you use FP16 and things like that. Okay. Now the key difference between the two F16 and BF16 is how they allocate bits to the exponent and fraction. So BF16 is for broader range handling without affecting the computational accuracy, but it supports only A100. Okay, so if you look at BF16, you need Ampere architecture. So I'm going to write A100 GPU. It has a computability with that. Ampere generation or the more recent one. Okay, if your GPU is compatible, I recommend you use BF16. If not, then use float 16. Okay, and yeah, that's what it is. And then we are okay with this. What else is left there? We have evaluation and save steps. I'm probably not talking about it. Pretty much self-explanatory. Okay. Yeah, and this is what it is, guys. I recommend you go through if you want to learn a bit more. I think we covered this training arguments part, but if you want to learn more about this, I recommend you read some article. There is a good article by Sebastian Rashka. I can share the link in description. You can go through his. He has given a practical tips article on fine-tuning LLMs using LoRa. But this is what I wanted to explain. I hope you got a bit of idea. I explained that these training arguments, and once you understand training arguments, it becomes a bit easier to fine-tune LLM because these are the variables. These are the things that basically improve the performance of your model. Of course, the data is the main thingy, the backbone of how good your data is. But yeah, that's what it is. Now, I think this concludes the experimentation, guys, on a guide on hyperparameter and training. That's all for this video, guys. I hope you understood the basic, the parameters and the details about the training arguments when you need to fine tune an LLM. Then you have to go through all of these hyperparameters to basically tweak these to try to find out an optimal values or the categories for most of it to improve the performance of your large language models if you're fine tuning a pre-trained or a base model or whatever. Now, this notebook will be available on my GitHub repository. You can find the link in description. Feel free to fork, extend, clone, whatever you want to do that with that. And if you have any question, thoughts, or feedbacks, please let me know in the comment box. You can also reach out to me through my social media channel. Find those information on channel banner and channel about us. If you haven't subscribed the channel yet, please do subscribe the channel, guys. That basically motivates me to create more videos. And if you like the content I'm creating, Please like the video and share the videos and channel with your friends and to peer. Thank you so much for watching. See you in the next one.